In section 6.6, we're going to find that we can add, subtract, multiply, and divide functions or algebraic expressions much like we can with other real numbers. One thing we're going to have to watch out for is that, just like with any other division question, if I end up dividing a function by another function, I do want to make sure that we restrict the domain of our function that we're dividing by to make sure that we don't end up with that function being 0, just like we don't want to divide 0 with any other real number. So we will consider domain on these, but let's just get right into it with a couple expressions. We're told that our first function, f of x, is 4x plus 7. Second function, g of x, is going to be square root of x plus another x. And that means if I want to do something like add those two functions together, we can say it like this. F plus g of x is how I'd read that. I know that if I was to add those two functions together, it's really just like taking the first function, adding the second function, and just trying to combine my result, just like we would if those were just two separate expressions. So if I take that first function, again, f of x is going to be 4x plus 7. Take the second expression in our second function, that would be square root of x plus x. If I just add these together, it's just like with any other addition problem. I don't want to watch out for any like terms. Only like terms we do have here is the 4x and the x, noting that if I have the square root of x, I can't combine this because the other ones do not have a radical. So as long as I combine 4x and x, I do get 5x. We have a 7, we have a rad x. Actually, to get this in order, usually going to see the rad x next, and then finishing with our constant. And that is going to be, again, just the sum of those two functions, f plus g of x, adding all those together, just combining our like terms like we normally would. I can also subtract functions using the same kind of operation. So let's see. If I was to subtract, again, f of x minus g of x in that order, again, just like with any other numbers, the order of that subtraction is going to be important. Let's take our first function. So f of x is 4x plus 7. We want to take our second function, subtract it. So noting that we do substitute this in parentheses, we do want to make sure we're subtracting the entire function, not just one value or the other. So here when I'm subtracting, it may be a good idea to distribute that negative sign. We're subtracting the square root of x, but we're also subtracting x if I remember that I'm subtracting a positive. So if I combine like terms here, 4x minus x, just like from before, those are our only like terms. We have a negative rad x in the middle, and then that positive 7 is just our constant. This would be our sum, or sorry, not our sum, our difference if I subtracted, again, g of x from our first function, f of x. Since we're also told to consider the domains, again, domain, kind of like what it means for any function, just means what values I can substitute in for x to come up with a real solution. And with our first function, it could be anything. Again, x could be negative, could be positive, could be 0, doesn't matter. Same idea with g, except when I do see this radical, again, if I have a radical expression for x, we know that I can't substitute a 0, or sorry, not a 0, a negative in for that radical, because I can't take an even root of a negative number. So we can say for both of those functions, again, for the addition and for the subtraction, our answer is the same because of our second function, g of x, and even in our final answer, notice we still have that radical x. We know that x has to be at least 0 since our radicands, again, can't be negative. I can't take that even root with a negative number because that's not going to get me a real solution. So domain is going to be something we have to consider when we finish this questions. Looking at a couple more examples, the only thing we're changing here is the functions themselves. We change f of x and we change g of x, but otherwise we're doing those same operations. Looking for one example to add the two functions together, another example to subtract the two. Let's look at our addition example. Taking these two functions, adding them together just means, kind of like with our last situation, all we got to do is look for like terms. We don't actually have any like terms. Oh, never mind. We have a constant 8 and a constant negative 3. As long as I can combine those, 2x squared, x, not like terms, and if I'm ordering those in order from higher to lower powers, we're going to see that written in what we call that standard form as well. What we know here is that our domain, if we're considering that domain, is going to be any real number. Again, because if my first function doesn't matter, x will be positive, negative 0. Second function doesn't matter what I substitute for x, nothing's going to make that a non-real solution. And even when I add them, again, that's also not going to be any kind of restrictions I need on those values. I can use negatives, positives, 0. Either one is going to be a real solution for x. To look at my second example of subtraction, again, just like our last example, you do want to make sure when you substitute, you would substitute in parentheses with that second function. If you subtract g of x, yeah, we want to make sure we're subtracting the whole thing, not just one term or the other. And that's where we want to be careful that 8 minus a negative 3, just like with any other subtraction problem, becomes a positive 11 at the end of my question. Otherwise, we still have a 2x squared. Now we're just subtracting x rather than adding it. And again, we have a domain of all real numbers because, like in our last example, where there's no restrictions on f or g by itself, so there's also not going to be a restriction when I subtract those two. So if our last example covered adding and subtracting functions, now we're just going to see if we're able to multiply and divide functions as well. And if it works like any of the real numbers, I think we should. Trying that first example with multiplication, again, that's how I read this, is just f times g of x. Of x is just like that's my input to my function. And just like our previous examples, all I got to do is take my first function and multiply the second, just noting that when I substitute those in, we got to be careful about when I actually go through to multiply. So since I do have 4 terms here, this kind of stands out to us as a multiplication question where I would have to do something like foiling or the box method. Since we've been using box method, I'll stick with that with those 4 terms. So again, x squared, -9, and an x and a positive 3. If I'm going to multiply to fill out my squares, I get x to the third. Kind of hard to read that, but yeah, x to the third, -9x. This would be a 3x squared, and I just finish with a -27. Since none of these are actually like terms, it looks like that's just going to be our final answer for that f times g of x. We have x to the third, ordering this down in terms of our powers. X squared is next, then that linear term, and then that constant. And if I'm trying to consider my domain on this question, again, since there's no restriction for either f or g, when I multiply those together, there's not going to be a restriction either. We can say for our domain, this is going to be all real numbers, because it doesn't matter what I substitute in for x. Could be positive, could be negative, could be 0. Any of those would give me a real solution if I multiply those two together. If I was to divide, division, a little bit more straightforward on this question maybe because we don't have to do that box method, but let's see if we can simplify this. F divided by g, let's list that out. Again, f divided by g of x, I would take first function and just divide by the second. Just like with subtraction, it does matter the order. So if I was to take x squared minus 9 over x plus 3, part of this actually calls back to Algebra 1. We do want to make sure that we're able to simplify this function completely, and that means if I have what we call this difference of 2 squares, we could actually factor this out as the sum and difference, kind of like with conjugates that we've seen. If I was to use the difference of 2 squares, it is going to factor as a term of x plus 3 and a term of x minus 3. So if I factor it this way, we're also able to simplify this function. If I have x plus 3 on the numerator and denominator of my fraction, it looks like those parts will just cancel. So actually the simplest form of this is just to write this as x minus 3. That is going to be, again, just the division of those two functions. But if I'm considering my domain, let's consider that as well. Domain, again, there's no restriction on the f or the g functions by themselves. But noting to my previous example up at the top of the page, last page rather, if I divide by a function, I want to make sure that we're not dividing by 0. So I need to know that if x plus 3 cannot be equal to 0, solving that for x, we know that the restriction for my domain is that our x value cannot be equal to -3. So much like with any other division question, if I want to avoid dividing by 0, we want to avoid using an x value input that's going to give me 0 for the bottom of that function. And even though it actually simplified for my final answer, notice that we don't actually have x minus 3 divided by x plus 3 in my simplified form. We want to use the original form when I substituted that in. That's going to determine my domain, so even though those parts simplified out and they kind of canceled from the top and the bottom of our fraction, if it was originally a part of my question, I want to make sure I factor that in for a domain on that function. Trying that with a couple more examples. Again, if I have to multiply or divide with two functions, we just want to check, kind of like have box method again with that first example, just because if I have, like we saw in the last example, 2 terms in the first as a binomial, 2 terms in the second, I just want to make sure we're multiplying in our box, much like we did that previous example. And like what we also seen in that previous example, none of these end up being like terms, so we can just write out those 4 individual squares for those results. And much like our example again from above, no restriction on our domain because f didn't have a restriction, g didn't have a restriction. We could use any x value and those would be a real solution. So when I multiply, it's still going to be a real solution as well. If I'm to consider the division question, it looks like I can just take the first function and divide by the second, so that's just f on the top and g on the bottom of that fraction in the numerator and denominator. In this case, we actually can't simplify as we did from before. If I have a difference of squares, I could simplify that as, again, a sum and a difference. But if I have the sum of 2 squares, there's actually no way to put that into a simpler form. So since this is as simplified as I can get it, and there's not going to be any kind of cancellations, we do also want to consider that my denominator, again, for my function domain, can also not be a 0, or as we saw in that last example. But if I was to try to find a solution here, or find a case where x is going to make a 0 as an input, we actually don't have any case where I can take a square root and end up being -1. So since there's no value of x that can make that denominator 0, our domain is actually still going to be all real numbers on this question. So again, on the last situation, if I plugged in -3, when I used that original fraction, that would have given me a 0 on the bottom. But since x squared has to be at least 0, it's not going to give me a negative answer. There's no way I can get the bottom to be 0 here, so my domain actually is going to be all real numbers still. So I'll just summarize the next couple of passages. You guys can always read through it further, but when we talk about composite functions, essentially that just means we're taking one function and we're substituting that in. It's kind of like plugging directly into another function, and then trying to see if we can simplify the result after that. So is going to be good to get used to the notation. We read this as g of f of x. Seems kind of confusing, but again, that just means we take g, we plug x into that function, and we try to simplify from the inside out. So again, if we're noticing the order, we simplify x first, and then we use that to solve for our second function. Trying that with an example, if I was to take, again, what we call this composite function, trying to find g of f of x, and again, notice that the order is going to be important. That means that if I start with this function g, I can just take the function f of x and substitute that in and try to find a solution. And notice that we do have two different methods of solving it. In our first method, we can simplify this function first. We can substitute -3 into our function f of x, figure that out. So if I find function of -3, I know that's just going to be -3 minus 5. So if I get -8 from that, I can then take that and substitute it into my g function, because again, that's what I'm looking for. I'm looking to take that output from my first result and plug that in for my next input. So now if I'm looking for g of -8, that means I can take -8 and substitute it in now that I'm using that different function. And -8 squared is just going to get me 64. 64 would be that final result, again, if I'm looking for what we call that composite function. The other method, and this doesn't work great here, but it does work better in some other examples, would be to simplify both of these functions first. So if I want to find g of f of x, again, that's how I'd read this, g of f of x. That means I can actually substitute this function directly in without simplifying first, and then we can figure out what that -3 input is going to be later. So if I figure out g of f of x, again, that's taking this function and substituting it directly into g. That means if f of x is x minus 5, and then g of x, I take that value for x and I square it. That's like just saying if I want to find the f function as an input, I can plug in x minus 5 where I see the x in that original function. G just means that I'm going to square that afterwards. So what this would mean is that I would have to use like box method, FOIL method. I'm going to simplify that a bit and just say that this would be what I would get as a result from that box. It is also helpful from Algebra 1 if you kind of know some shortcuts and multiply that out as a perfect square. But if I know that this is going to be x squared minus 10x plus 25, that again is the function just in general in terms of x. If I want to find the function in terms of -3, now I can take my step and substitute after we've written that function out. So -10 times -3, and then a plus 25. And in this example, if I get something like 9 plus 30 plus 25, this is another way to get me the same result that we found from before. This is another way to find out that we just get a 64 as a result. So notice if I did reverse the order on this next example, if I take f of g and I tried to find the same sort of solution, that would be, again, taking this function and substituting it in for f of x instead. And let's try that method. I think method 1 worked a little bit faster in the last example, so let's try that here. Again, if I take -3 and if I plug that in for g of x first, I'm going to find g of -3. So in g, I just had to square that result for x, so I just get 9. And now that we know that 9 is the answer to g when I plug -3 into that function, now I'm just going to take that result and plug that into f. So f of 9, that means I just take 9 minus 5. That should be pretty straightforward. 9 minus 5 is just going to give me a 4 for that result. Again, this does work with our second method. That would just mean that if I'm trying to find, again, that function first, so in this case f, and then substituting g in first, g is relatively simple. Again, that's just like saying x squared. So that function is pretty easy to work through your second method. If it's just x minus 5 for my function f, and g was just x squared, that x squared is just replacing the x from that f function. And now if I want to substitute in my -3, -3 squared minus 5 would mean I get 9 minus 5. That is another way to get 4. So yeah, when you ever see these kinds of composite functions, g of f, or if I reverse that, f of g, notice that we don't get the same solution based on whichever order I have that in. It's going to matter. And again, it doesn't really matter which method you do choose. You just want to stick to whatever method you use best. Some of them work better on different questions. Again, this is a little bit harder method based on that first question, but easy enough if I use my second two functions. Something like x squared minus 5 in that order, I could just take -3, plug that in, and then get an answer for 4 using either of those two methods.